Today we are going to look at electromagnetic induction. So the first thing we need to do is remind ourselves that if a current is flowing through a wire, a magnetic field will be generated. These magnetic field lines will be in concentric circles, and another name for magnetic field lines is flux lines. So when current flows through a wire, it creates a magnetic field. Electromagnetic induction is essentially the opposite of this. So imagine if you have a magnet, a normal bar magnet, and a wire near it. The bar magnet will have a magnetic field surrounding it with magnetic field lines going from north to south. If you pass the wire through the magnetic field lines, the electrons in the wire will move to one end. This induces a potential difference across the wire. Another word for potential difference is voltage, and a key word here is induces. So, next thing that we're going to talk about is electromagnetic induction in a coil of wire. As you move a magnet through a coil of wire, the magnetic field changes. This change in the magnetic field induces a voltage across the coil. So, if you place the coil in a complete circuit, a current will flow. And we can incorporate a galvanometer, which will allow us to measure really small amounts of electric current. Essentially, if you put a bar magnet into a coil, a potential difference will be created and therefore a current will flow. Note, the key point for this is that the direction of the voltage is dependent on the way you move the bar magnet. And the bar magnet has to be moving for a potential difference to occur. So, the next key question that we're going to ask ourselves is, how do we know which direction will the voltage be induced? Here, I have a galvanometer attached to a coil of wire. Notice that there is no source of electricity here. And when there's no bar magnet moving, or in the presence of the coil of wire, the galvanometer is at 0. However, if we get a bar magnet and notice that its orientation is north to south, if you move the bar magnet into the coil of wire, a voltage is induced. And the galvanometer will deflect, or another word for this is move. So as you can see here, the little bar on the galvanometer will have moved to the left. Again, if you move the bar magnet this time in the opposite direction, deflection will occur again. This time in the opposite direction. So this time the bar will move to the right. For this to occur, these deflections to occur, the magnet and the coil has to be moving. Okay? It will not occur if the magnet or the coil is not moving. It requires a change in the magnetic field. Now we need to ask ourselves, what would happen if you flip the magnet around? So if you change the polarity. So again, we have the same equipment as before. This time the south pole is moving into the coil of wire rather than the north. So south to north this time. If we move the south in this time, the deflection will move in the opposite direction. So unlike last time where I moved to the left, this time we will move to the right. And the arrow will move to the right of the galvanometer. Again, if you move the bar magnet out, the deflection will occur, but this time in the opposite direction. So, some factors to consider here that affect the size of an induced voltage. If you want to increase the voltage or current, you could do one or more of the following. Firstly, add an iron core inside the coil. Secondly, increase the strength of the magnetic fields. Thirdly, increase the speed of rotation, so increase the speed at which you move the bar magnet in and out, or if you're moving the coil, the speed at which you're moving that. And fourthly, increase the number of coils. If you want to decrease any of these, decrease any of the following four factors will reduce the voltage induced across. How can we use electromagnetic induction to create an AC current? So here we have a soft iron. It is in a horseshoe shape or in a U shape. And around it we have a coil of wire. We are going to place a magnet inside it with the north and south. Note that the north here is on top and south is on bottom. And as we should be aware, the north magnetic field lines will go through to the south, and it is passing through the iron core. This magnet has also the ability that it can rotate, so we can twist it around. As the magnet moves, it induces a voltage on the wire, causing a current to flow. So as the magnetic field lines move from north to south through the iron core, a current will flow through the wire because of an induced voltage. Once the magnet does a half turn, however, the polarity of it changes. So if we have a little look at this again, you'll notice now that the south is on top and the north is on bottom. Remember, the magnetic field lines have to go from north to south. So the direction of the magnetic field through the coil and the iron core is reversed, this time going in the opposite direction. When this happens, the voltage induced reverses as well, so the current flows in the opposite direction. If you keep on rotating this magnet in the same direction all the time, what you will get is that a current will keep on changing its direction for every half turn. This will be an alternating current, or another name for this is an AC current. Hopefully this is of some help to you.